Thank you all for coming. I'm Michael Osman of Great Scott Gadgets, and this is Jared Boone to my right of ShareBrain Technology. We are both open source hardware developers, and we're here to talk today about the HackRF project. Hikari and Gio and Tim were kind enough to give us this slot, I think, because they think this is a cool project just like we do, and that it's important for our community and something that you guys would all like to hear about. So I hope they're right. HackRF is a software-defined radio project. It's really a hardware project for software-defined radio. And software-defined radio, how many of you guys have heard of software-defined radio? Most of you? Excellent. We'll go over some basics very quickly, and then we'll move on to the more interesting stuff, just to make sure everybody's caught up. Software-defined radio is the application of digital signal processing to radio communication systems. And it is, I like to, when somebody asks me, what is software-defined radio? How do you explain it to somebody who's brand new? The way I like to explain it is to make the comparison to digital audio systems and software audio systems that we've all seen over the last couple of decades change. Digital signal processing is using general purpose computation to deal with signals that are digital, and a digital signal is simply just a sequence of numbers, right? And we often we represent digital signals often with a graph like this, where we have like a series of dots that have sometimes a stem to time axis or x-axis of some kind. But all it is just a sequence of values. An analog signal like this blue line can be represented by a digital signal, and we can convert an analog signal to a digital signal with an analog to digital converter or a sampler, and we can convert a digital signal into an analog signal with a digital to analog converter, which simply allows you to convert back and forth between the analog domain and the digital domain. And we've seen this happen with audio systems, for example. Back in the old days, we had all kinds of analog audio systems. Everything was analog. We had analog recorded music. We had analog telephone systems, and so forth. But over time, through like the 70s and 80s, we started seeing more and more digital audio systems, like CDs, compact discs, for example. And gradually these things, digital phone systems, became more and more popular. But there was a more sudden change, I think, that happened in the 90s. And the big change was when general purpose computers became powerful enough to be able to process digital audio signals. And we saw things becoming enabled, like MP3 file sharing and hard disk recording, where people could afford to create a high quality recording studio in their own home. This was a major leap, I think, a big explosion. And so where some people talk about a digital audio revolution that took place over time, I think of it really as a software audio revolution. The change from analog to digital happened gradually over many years, but what happened suddenly were these technologies that were enabled by people being able to do this digital signal processing in software on their general purpose computers. A lot of crazy things happened at that point. And we're just getting to the point now where computers are fast enough to be able to process radio waveforms in the same way that they were processing audio waveforms back then.
So digital data communication followed a very similar evolution to audio, as Mike just described how audio has evolved. Consider telephony modems of the 70s, 80s, and 90s. They modulated a carrier with data. The modulated data was audible. Of course, it had to be audible to go over a phone line. So at first, modems used analog technology to modulate and demodulate the data. In the 90s, it became commonplace to use digital technology to actually modulate and demodulate the signals over the telephone line. The telephone line was connected to an analog to digital converter, a digital to analog converter, and dedicated digital signal processing chips were used to achieve the amount of performance required to do the math, to do the modulation and demodulation digitally. This was great because new software could upgrade your modem. You don't have to actually buy new hardware. You would get new software, you would flash it onto your modem, and now you could do 33.6 or 56K, and you could download your porn at 5K a second instead of 3. It was great. I remember those days well. When computers got fast enough, modems evolved into what some people called WIN modems. And the focus there was on making the computer's processor do the same signal processing that the modems were doing, except now it was being done with a general purpose processor in Windows driver level. Modems were reduced to just being analog to digital, digital to analog converters, and a line interface, and that was basically it. There was really no modem per se, no modulator, demodulator on the modem card itself. Upgrades for those kinds of modems was just a matter of downloading software and installing it on your computer instead of even flashing it onto the modem hardware. DSL and cable followed a very similar, or were enabled by this digital modulation technology. The line interface, of course, is different because you're going over a copper pair that does not have voice constraints that a telephone pair does. So now you were talking about megahertz wide bandwidth available through these modems, and analog to digital and digital to analog converters, as a result, got much, much faster, and the amount of signal processing required to do that kind of work went up. But fortunately, computers have been able to match that over time. So like modems, radio started out in the analog domain. They've become digital as digital signal processing became more and more viable, and radios are becoming software more and more every day. So let's look at how you might build a digital radio, a software radio. You would have an antenna, like any radio would, and then you would immediately hook it up to an analog to digital converter and digitize the radio signal directly, feed the resulting samples into a processor, and run whatever algorithms you need to modulate or demodulate WiMAX or Bluetooth or whatever technology you're interested in. Similarly, if you want to transmit, you would use a CPU and you would run a modulation algorithm to generate a stream of samples that would go out through a digital to analog converter and out through an antenna. So as you can imagine, this has an incredible advantage for flexibility. We now have a single piece of radio hardware that can act like any type of radio you can imagine. And it's purely a matter of what software you run on it. You could, in fact, use a single radio to receive multiple different bands of signals, TV, Bluetooth, across various different spectrum, and demodulate it all with one radio simultaneously. You could also, by using that technique, consolidate a bunch of different radios, like the radios that we have in our cell phones, into a single radio. You could take Bluetooth and Wi-Fi and GPS and NFC and cellular and bring them all into a single piece of hardware that just runs software on the resulting sample stream in order to decode or encode whatever signals you need to transmit. So software radios also have a huge advantage in terms of reconfigurability. As new protocols and modulation techniques come out, all it is a software update. If you want to do fancy new adaptive filtering to pull signals out of ever-increasing amounts of wireless noise, it's a software update. If you want to operate on different frequencies, theoretically you could just update the software to operate on the new white spaces frequencies, 700 megahertz, that kind of stuff. Most importantly, perhaps for this community, is you can also release bug fixes. So if your implementation of a particular wireless protocol turns out to be flawed, it's not embodied in a piece of hardware that you can't change without giving someone a new piece of hardware. You can deliver a software update and fix that problem. And lastly, having software radio technology enables a lot of new hacks because it allows such a low level of access to what's actually going through the air that you can get down to the very lowest levels and manipulate it to whatever devious ends you desire. And of course, all these software modifications can easily be shared and distributed online. So software radios are they're still really not extremely commonplace. They're kind of expensive on the whole because you've got this trade-off. You can build radios for specific technologies still more inexpensively than you can build a general piece of digital software radio hardware. As time progresses, Moore's law will enable software radios to come down in price, consume less power, be smaller physically, and be embedded in more and more devices, and enable all of these other advantages. So as computing power improves, as I said, the software radios will become more and more commonplace. As new radio technologies are developed, they'll be prototyped on general purpose software radios, and reference implementations will be distributed along with the new standards, and people will be able to pick them apart and improve them, find flaws in them, and iterate on them. And also wireless security tools will definitely be software radios going forward because of the vast flexibility that software radios provide. As I said, having really low level access to what's actually being transmitted and being able to see at the very lowest levels what's being received provides just an incredible amount of detail as far as exactly what's going on with the signal, how you can manipulate it at the very lowest levels, and find new vulnerabilities.
So I find that I'm constantly reminding people about the history of Wi-Fi security. Anybody remember what Wi-Fi security was like 10 years ago? What? What?
There's two words.
What security? Wi-Fi has changed so much over the years. We broke it, we fixed it, we broke it, we fixed it, we broke it, we fixed it. I think Wi-Fi security is pretty good right now. Some of you out there might argue with me, but you can go to any electronics store, buy some Wi-Fi equipment, and set up a network that is fairly resilient to over-the-air attack today. Could you do that 10 years ago? No. And of all the problems that Wi-Fi, all the Wi-Fi security problems that we've seen over the years, what do you think is the most severe? Anyone? Open, unencrypted networks, default passwords, Wi-Fi protected setup, anyone? Wireless equivalent privacy, anyone? WEP? Personally, I think WEP is the worst of all the terrible things that have happened with 802.11 security over the years. WEP was really bad, and on top of being really bad, it gave people a terrible false sense of security. And when Wi-Fi first came out, did we know that WEP was broken? In academic circles, at least, yes, we did. There were theoretical weaknesses that had been pointed out very early on that the manufacturers just ignored. Why did they ignore them? Time to market, money, I heard somebody say. And I think that overall, people just didn't take, in particular the manufacturers, just didn't take the vulnerabilities seriously. When did they start taking them seriously? They took them seriously when they were being exploited and when they were being practically demonstrated. When there were theoretical vulnerabilities, they were ignored. When they became practical vulnerabilities, well, then they were addressed. And the tools that gave us all the ability to test these vulnerabilities and demonstrate them were Wi-Fi adapters that were capable of monitor mode and raw frame injection. Those were the two things, the two capabilities that we, the information security community, needed in order to make those theoretical vulnerabilities practical and actually affect change. And this is Wright's law. The vulnerabilities will continue to be ignored until tools are available to demonstrate those vulnerabilities. Well, nice.
These things are supposed to lock.
Check one, check two. That's a new one for me. I don't think that's ever happened to me. So we needed monitor mode and raw frame injection in order to affect change in Wi-Fi, and we got it. And Wi-Fi, for all its faults, has improved by leaps and bounds over the years. Has that happened with other wireless communication technologies? Not so much. Not so much. There are a few that have gone through some change, but I can't think of any single wireless communication technology that has gone through as much positive change for security as 802.11 has over the last decade. Well, I think that we can do better. And I think that we can study more wireless communication protocols, more technologies. We can find flaws in more of them. We can fix flaws in more of them. We can build new systems and build new technologies if we have the tools to do it. What we need is very simple. We need monitor mode and we need raw frame injection for everything. What if we had monitor mode for every wireless communication technology? What if we had raw frame injection for every wireless communication technology? This is the promise of software-defined radio. And in the information security community, we've seen this. Software-defined radio is a technology that is proven for wireless communication security research and development. How many of you guys have seen software-defined radio used for some cool hack? GSM, Bluetooth, Zigbee, implantable medical devices, tire pressure monitoring systems in automobiles. I mean, the list goes on and on and on. How many of you have actually done those things? There aren't very many hands going up in the room. Why is that? I think the main reason for that is that the technology the software-defined radio technology has been accessible just to the point where a small percentage of us who have research budget are able to use that technology. And thinking back into the Wi-Fi days, well, when the small percentage of people who had research budget could afford equipment that could, say, monitor and decode packets from a Wi-Fi network, did we see change? Not really. When we saw change was when all of us could afford the technology, and the technology was accessible to us for monitor mode and raw frame injection. And that's really our focus with the HackRF project. We're trying to build a tool that enables everyone in the information security community to kind of take part in this exciting new world. I'm focusing on what I want for my own wireless security research. I want something that meets my needs, and I think meets the needs of the security community as a whole. So I used to try to carry around equipment that would allow me to, transmit and receive signals on like every different frequency, that every type of target device I ever encountered. So I could hack on them. But my wallet looked like this, and my backpack looked like this, and my girlfriend looked like this, and I think some of you have had similar experiences. There are a lot of interesting targets out there. There's a lot of stuff running at operating frequencies below a gigahertz, and your TourCon badge is one way that hopefully you could even today start hacking on some stuff below 1 gigahertz. But there's also stuff between 1 and 2 gigahertz, like decked cordless phones and GPS systems, mobile phone networks, all kinds of things. There's a ton of stuff in the 2.4 gigahertz ISM band that a lot of us will be interested in, including Bluetooth, Zigbee, Wi-Fi, etc. And there's even stuff in the 5 gigahertz band that I think will become more interesting over time. I would like to have one device in my bag that does them all. There are a lot of different target bandwidths we might be interested in. There are certain devices certain wireless systems that we really only need an acquisition bandwidth of less than a megahertz to capture. But then there's stuff around 1 megahertz, 2 megahertz that might be interesting, like Bluetooth and Zigbee and so forth. And then there are some technologies that, especially mobile phone technologies, that are in like the 5 to 20 kind of megahertz range. And there's a little bit of stuff higher than that, but pretty much all the stuff that I'm really interested in being able to hack on is 20 megahertz in bandwidth or less. And so I would like to have one device that does them all. I would like to have one device that both receives and transmits. I would like it to be portable, so I can just stick it in my bag and carry it with me everywhere I go. I don't want to have to carry around wall warts and power strips and look for a power outlet every time I encounter a new wireless communication system that I want to check out. And I want this device to be something that is affordable enough that I only have to buy one of them, and it's something that any laptop owner can afford. Perhaps most importantly, I want this device to be open source. Now, Jared was talking a little bit ago about how software-defined radio allows us to reconfigure radios and upgrade radios using software modifications, and how those, because they're software, they're easy to share. The software-defined radio community as a whole includes a lot of people who are working on open source software. And the information security community includes a lot of people working on open source software. There isn't as much overlap there as I would like to see going forward. I think that the information security community values open source software. I know I do. And there's a growing awareness, I think, that we can get some of the same benefits from open source hardware. There's more and more open source hardware being developed within our community and outside of our community that I find very exciting, and I know Jared does too. I mean, to the extent that we've both dedicated our lives to building open source hardware. So we think that it's very important to not only have open source software tools for software-defined radio, but to also have open source hardware tools for software-defined radio. And that's one of our goals for the HackRF project. Now, in order to meet these goals, we have some trade-offs that we're willing to make. Traditionally, the kind of conventional wisdom in the software-defined radio community is that we need to represent digital signals with 10 to 16-bit numbers and 10 to 16 bits per sample. That's the dynamic range. And we think that we can get by with less than that. We think we can get by with 8 bits. And we were operating on that assumption already when some TV tuner solutions came out. How many of you guys have seen the TV tuner software-defined radio stuff? Pretty cool stuff, huh? Those have actually demonstrated to a lot of people how much can be done with 8-bit samples. And so we're pretty excited about what's going on there, and it kind of validates our design decision. We can also live without a lot of digital signal processing capability in the hardware itself. The reason we can do that is because we're carrying around laptops anyway, and our laptops have general purpose CPUs in them that are capable of a tremendous amount of signal processing. And so we can live without having the digital signal processing capability on the board itself. We can live without full duplex communication that's transmitting and receiving simultaneously. We want to be able to transmit, we want to be able to receive. We don't necessarily have to do it at the same time. Most of our needs in the field and in the lab can be met by just transmitting at one time, receiving at another time.
So, to address all these requirements that Mike spoke of, here's what we've been working on. This is the HackRF jawbreaker. Got one right here. It's a small USB-powered, affordable transceiver that tunes a vast range of frequencies. In fact, it's been tested down to 30 megahertz and up to 6 gigahertz. Handles a considerable amount of radio bandwidth and won't earn you a TSA cavity search, although we make no guarantees about that. So at a high level, the architecture of the design is what's called a dual conversion architecture. That is, that the target signal is shifted twice on its way to becoming digital and being sent to or received from the host. This technique vastly increases the range of radio spectrum that HackRF can tune. So that's how we succeed in covering 30 megahertz to 6 gigahertz. And then there's a microcontroller which is used to shuttle the data that's captured or that needs to be transmitted between the radio portion and high-speed USB to a host computer, which is used to do the bulk of the signal processing. Zooming down a little bit into the specifics, there's a wideband front end which is made from a RFMD RFFC 5072 mixer. Basically what it is it's an oscillator with a piece of mixing hardware that takes signals from that very wide band of frequencies, 30 megahertz to 6 gigahertz, and shifts them into the 2.4 gigahertz range, where we use a very inexpensive, highly integrated chip, which is designed specifically for 2.4 gigahertz. That's the IF Xceiver there. That device is connected to an analog to digital converter and a digital to analog converter, and that's where the boundary between the analog and the digital portions of the design exists. From there, the converters are hooked up to an XP processor. It's an ARM-based processor, and out the other side go the samples, or in the other. The USB carries the samples back and forth between the MCU and the host. So here are some more details on the specifications. As I said, it has high-speed USB 2, operates between 30 megahertz and 6 gigahertz, but we're also working on getting the sampling rate up. So at the moment, we're able to sample about 10 megahertz worth of spectrum, and that's primarily because of limitations in the USB code right now, I think, and also some of the clocking schemes that we have on the board. We're hoping to lift that to 20 megahertz. The hardware's certainly capable of it. I think it's just a matter of getting a few details sorted out in the software that runs on HackRF. It can transmit or it can receive, so you've got options there. Runs off of USB, and I don't know, have you tested the total power consumption at the moment? I haven't.
Not recently.
Yeah. So, of course, trying to keep it within the USB 2 limitations of 500 milliamps over the USB. So far we haven't had any problems, but we should probably do a formal test of that. And most importantly, everything about the design is open source.
So I'm sure many of you have heard of DARPA's Cyber Fast Track program. I hope so. Everybody, you know about it? because you should. It's a really cool program. And we're happy that our project, our HackRF project, has been supported by the Cyber Fast Track program. We think it's pretty cool that that the United States government and the Department of Defense in particular sees fit to fund a project like this that is giving away open source hardware and software design to the community. 100% of this project is open source. It's a pretty big project for us. It's like a year long and a couple $100,000, but it isn't a really big project for the Department of Defense, right? And what's great about the Cyber Fast Track program is that it enables what would be maybe too small projects for the Department of Defense to invest in. It enables individuals and small groups, small companies, hacker spaces in our community to propose projects and get them funded. And you can propose them on your own terms. And our terms were that we were going to give absolutely everything away. And if they think that that is something that's going to be value to the community as a whole and to whatever their goals are, then they'll fund that. And it's a tremendous opportunity for all of us. So if you've thought about maybe starting a research project, but you weren't sure how you're going to find the time or the money to actually do the project, this is a great program, and you should really consider submitting something.
So, as I mentioned a bit earlier, this project is entirely open source. I think we both feel very strongly that communication technology that we depend on, every second of our lives virtually, should be open and well understood and well investigated. As information security enthusiasts, I imagine you would appreciate that. So you can check out the hardware, firmware, and host software and modify it to do whatever you want. We're using GitHub to host the source code. There's also design files and design notes kept on the wiki. So if you wanted to read some of our musings around exactly how the hardware has been configured and how it operates, that's up there too. Communication between the various people on the team has been primarily through IRC with a few occasional emails bouncing back and forth. I've been amazed at the wealth of experience that happens to hang out on the channel, Care Bear in particular, and his all-knowing USB experience. So what I find useful is I just go in the channel, I just kind of yak about whatever it is I'm doing and wait for the clever, informative, or snarky responses to come back. Invariably, they're useful, even if my ego might get a little bit bruised in the process. So if you're interested in helping out with HackRF, probably the best thing to do is to come into the IRC channel, tell us what you want to do with HackRF, what you'd like to do, what you want to do with HackRF, what you are doing with HackRF if you happen to have one, and there's more about that later, and how you might contribute to HackRF. If you're someone who only knows software, well, there's actually a lot of software that needs to be written. If you know hardware and you want to critique the design and talk about improvements, that's all great. So I want to talk a little bit about the tools that we used in HackRF. To start with, doing the hardware design was done predominantly in KiCad, which is an open source schematic capture and circuit board design software. Mike did the bulk of that work, in fact, all of that work. We used GCC and GDB for ARM to develop the firmware for the HackRF processor. Used OpenOCD for debugging the processor over JTAG or serial wire. DFU util for downloading code to the processor over USB. Python and C have come in handy in order to interact with the device over USB, and we're also using Make and CMake as our make systems throughout the project. There is one little exception to the open tools claim, and that is that we have a programmable logic device from Xilinx on the board, which we're hoping to eliminate in a future revision of the board. And what that does is it moves samples back and forth between the A to D, D to A, and the processor. But unfortunately, the Xilinx part requires closed tools, which are available for free as in beer from Xilinx, but still aren't technically open. So the hardware design process was, Mike did the hardware, the schematic entry, developed the general architecture, did the circuit board layouts, and would consult with me along the way about things that he was thinking about, things that he was concerned about, and we go back and forth on that. Over several months of design, we did a bunch of iterations, but this was entirely expected. We didn't exactly know how the end design would wind up. We had a bunch of ideas, we wanted to try them out. So we used a very modular approach where we would build just the digital portion and then just the 2.4 gigahertz and digital to analog, analog to digital section, and then another board that had just the wideband front end on it. And that allowed us to swap out individual pieces should one of them not work the way we want and require a redesign. We didn't have to go and redo the entire design all at once. So this project is also 100% NDA free. There were a lot of interesting parts that we saw out on the market that did really high bandwidth software radio type stuff, but unfortunately they were covered by NDA, so you couldn't get the documentation for the part unless you signed an agreement not to tell anybody else about it, which is of course not very compatible with A, open source, and B, getting a large community of people to help make this technology really available. So we steered clear of NDAs. Oh, is there a question? Yeah. Yes, go ahead.
With GNU Radio, you need like a suitcase of antennas in order to hit all the frequencies. How do you guys get around that?
We don't. Yeah, you still, I mean, antennas. Oh yeah, so the question was, with GNU Radio, or frankly any other radio, it really behooves you to have an antenna that's designed for the particular band of frequencies you want to work with. So we can't really address that any better than anyone else. There are probably clever antenna technologies coming down the pike that might address that eventually, but really we're on the same footing as GNU Radio, all the hardware associated with GNU Radio, where, yeah, if you want to deal with 2.4, it's good to have a nice little stubby antenna. If you want to deal really low frequency stuff, it's nice to have a really giant antenna. So yeah, we really don't address that. So let me talk about the digital portion of the project and its impact on sort of our open source philosophy. We had to write a lot of code that runs on the HackRF from scratch. Ordinarily, an ARM vendor will sell you the processor, and they'll also give you a library of code to work with their processor. And invariably, the license will say, you can't use this on anything but NXP parts, which to some extent is fine because this code is usually very specific to the processor that they're selling. But there's still a lot of commonality, in fact, more so all the time. I'm amazed to find that Freescale has a USB peripheral on their ARM processor that appears to be exactly the same as this one. So all the work that I did, for instance, making the USB stack on this ARM work could be reused on this particular Freescale part, except that if I were to use NXP's version of this USB library, I couldn't do that. So we spent a lot of time rewriting code that the vendor, NXP, provides for this chip, but under a license where we could distribute it and people could use it potentially for other processors should that code actually work for other processors. Moreover, the work that we've done, we've contributed back to a project called LibOpenCM3, which is open Cortex M3 ARM library of code. So I want to point out that we are not, you may have some impressions, maybe we're electrical engineers. We are not. This project was a lot of work and was very technical, involved hardware design, firmware design, software design, but neither of us are formally trained in electrical engineering. But we did not let that stop us. I think most importantly, we are persistent and we saw a need for something that we wanted ourselves. So we hacked our way through the project, building on others' work. You know, there was a lot of open source technology and knowledge that we could build on top of. We learned a ton along the way, and we want to share what we've learned with the rest of the community so that you can build on it and share what you learned.
I think this would be a good time to do a demo.
Yeah.
And I'm going to let Jared set that up because I actually don't even know what he has in store for us. So the way this has worked is that, you know, I've done most of the hardware design, and he did, you know, pretty much every hardware design decision that I made along the way, I consulted with him on. I said, what do you think about this chip? What do you think about that chip? I'm thinking about doing this. What do you think? And then I would make a design, and I would make a schematic, and then I would send it to him, and then he would critique it and say, no, you're doing it all wrong. And I would revise it, and then I would do a board layout, and I'd send it to him, and then he'd tell me the 50 things that I did wrong. And then I get the board made, and I would test it, and then I would find out how it was broken, repeat. And so I've been so focused on hardware that the software along the way has yet to catch up. One of the ways that it has caught up very recently, just within the last couple of weeks, is the work that Jared has done on the USB interface. He was talking about the USB stack that he's written for the LPC 4300 microcontroller. I mean, a few weeks ago, even a couple months ago, we had signals going from the antenna received all the way through the entire piece of hardware, all the way to the microcontroller, and then stop. And then we could transmit stuff from the microcontroller all the way through everything out to the antenna and over the air. But that last mile between the microcontroller and the host computer, that USB connection, that was something that we didn't have working until just very recently, and it's thanks to Jared's efforts primarily there, and some help from people who've been hanging out in our IRC channel too. So we don't have a lot of host code written yet. Our goal is to create an interface for GNU Radio. GNU Radio is an open source software framework for developing software radio applications. And it supports a variety of cool hardware already. And it's very popular within the open source software radio community. So that's really our target, is to make HackRF easy to use with GNU Radio. And we've just got it working very, very crudely within the last several days. Jared is setting a demo up here, I think, where he's going to do an acquisition. He's going to do a receive. Yeah, there we go. So, Jared, why don't you explain what you're doing?
Okay, so I've got as I said earlier, we did a whole bunch of modular board designs first. So this rat's nest of boards is one of the very first prototypes. Mike's got a slightly more fleshed out version here. It has two of the same boards that this does, but it also has the RF front end, which enables the 30 megahertz to 6 gigahertz range. This board only has the 2.4 gigahertz capability. So what I've done is I've tuned this radio to 2.441 megahertz or gigahertz, and I'm sending out 10 megasamples or 20 megasamples per second complex to GNU Radio, and then I'm graphing the resulting spectrum. And it's scrolling up slowly. This is a waterfall diagram of the frequencies around 2.441 gigahertz, plus or minus 5 megahertz. So the red line down the middle is 2.441. If it scrolled faster, you'd be able to see more discreetly the individual packets that were being received. But as it is, you just get these really strong lines. If I were to switch over to the time domain, we might even be able to see bursts of traffic here. Yeah, barp, blarp, blap. Yeah. So there we go. And just with this functionality alone, piped into GNU Radio, there's a tremendous amount of stuff you can do. If you check out cgran.org, I think it is, there's just a raft of really cool projects done with GNU Radio to decode everything from boats and aviation to, I think there is some Wi-Fi stuff. DECT, I think, is in there too. There's all sorts of stuff already implemented to some extent in GNU Radio that can run off of the samples that we're feeding out of HackRF and into the laptop.
Oh, we need to switch back to the other laptop here. Let's see. Does it work? Yay! So I want to tell you about our beta program. And this is something that we're just announcing here right now for the first time. And this is kind of our beta release. Even though we only have one finished board, more are being made. The one finished board is almost 100% correct as far as our testing so far. If you come up and look at it, you'll see a couple of little wires going across it that are little corrections. And so I made a new revision of that board just within the last several days, and I just got word yesterday that the first PCBs of that rev are being shipped to my home, so I'll be testing it next week, and if it's all good, we're going to proceed with manufacturing of a bunch of these. And you should have received at registration a little card that says something about a HackRF beta and has a little code on it. I'm pleased to announce that as soon as we have these things made, you will be able to use that code, redeem that code for a free HackRF jawbreaker. I know most of you thought that was part of a crypto challenge. It's not.
But it could be.
It could be, no. Yeah, please don't brute force me. So I want to point out that the reason we're able to give away hundreds of these is because of our funding from DARPA, from the Cyber Fast Track program. So I think everybody, we'd all like to give DARPA a round of applause. Yes, thank you, DARPA. Personally, I was just floored by this, that not only was DARPA willing to fund the development of this project, but also willing to fund giving away a whole bunch of these boards to our community. And it's really kind of exciting for us because, I mean, first of all, there is a growing number of open source hardware projects in the world. There aren't that many that are this complicated. This is a very, very challenging electronics project for us, and it's a complicated device that requires a lot of testing. A more traditional development process would probably take, twice as long and 10 times as much money. But what we're doing with DARPA's support is you taking our open source software development process and using it pretty much directly for open source hardware. And one thing that I haven't seen done before is a well-funded beta program where we can get a whole bunch of boards out to people and hopefully get some more volunteers contributing back to us, at the very least telling us what works and what doesn't. That's kind of a crowdsourced testing program that I don't know anyone's ever done with an electronics project of this complexity. And so we're excited to have the opportunity to kind of try something new there. So thanks again to the DARPA Cyber Fast Track program, and thanks to Bit Systems for managing being our contact for the Cyber Fast Track program and helping us out with this project. Thanks to Benjamin Vernew and Will Code. And these are a couple of people who just kind of showed up in our IRC channel and started writing code. And I was like, okay, I'll send you hardware. So I've been building hardware by hand to give to these guys who've been helping us out. I would like to build more hardware and get more volunteers, and now with DARPA's support, we're able to do that. Thanks to David Holton, who was the person who said to me, Mike, you've been talking about doing something like this for years. Why don't you just submit a project to CFT and get this thing done? And so that's what we're doing. Thanks to TourCon. TourCon has been supporting us all along, and for giving us, this venue to be able to talk to you and to announce our beta program here. That's really exciting for us. This is the URL for kind of the master URL for the project. Mostly, it's just a small page with some links to the really interesting stuff. This is where the information about the beta program will be announced. When the time comes that you'll be able to redeem those codes for your hardware. That's kind of the master place to look for that. It's going to be a few weeks. Some of the parts on the board take like up to 6 weeks to order, and we're just kind of starting the process now. So the actual assembly of the boards will probably be around December. So maybe you'll get a nice Christmas present. But we don't have a firm date yet on when we'll be shipping those. And do we have a little time that we could take a question or two? A couple minutes. Any questions before we go?
What kind of latency are you expecting on the final hardware?
Yeah, what kind of latency are we expecting? And this is a good question for all software-defined radio peripherals. There is a significant amount of latency just on the USB interface, right? So, and this limits our turnaround time. We're doing half duplex communication. So if we receive a packet and then we want to reply to it, how fast can we actually do that? I don't have a hard answer for you at this time, except that Jared might have a hard answer for you at this time.
Well, I wouldn't say hard, but I have been living with the USB stack for a fair bit, and if I were to sort of guesstimate based on what I've seen so far, that I would say sub-millisecond. It seems like the microcontroller we've got is capable of getting packets out on the next microframe of USB, and each microframe is 125 microseconds. So I would say there's certainly potential to get it down below 500 microseconds, possibly.
That's really cool. 500 microseconds is probably better than I was anticipating. However, keep in mind that a Bluetooth packet can be 200 microseconds long. So 500 microseconds, depending on the communication protocol you're working with, can be a problem. Also, you're going to have additional latency in the host computer where by the time it's figured out how to demodulate and decode a packet and reply to it and synthesize a new packet, that takes time also. So it's definitely something you should consider and think about for a given solution. We do have some digital signal processing capability in the ARM microcontroller. That wasn't a major design goal. Mostly we just want to get samples in and out. But it's a 200 megahertz Cortex M4 with some DSP saturation instructions. It has a floating point unit, and it has a Cortex M0 coprocessor. It's actually a dual core microcontroller. So some applications, you could probably actually do your DSP in there and not have to deal with the USB latency. And there was a question right behind you.
It's great that DARPA is willing to fund the production of a couple hundred boards, but are you able to tell us at this time, at the scale of producing, say, 1,000, what the cost is?
The question is great that we're able to make a few hundred for the people in the room, but what are we going to do beyond that? Right now, we're totally focused on just getting beta hardware out to people. And we're going to make a few hundred and get them out to everybody in this room and some more people who we hope will be able to contribute to the project. Beyond that, I do plan to turn this into a commercial product. And my target, or my rough target pricing for the Jawbreaker board or something similar to the Jawbreaker board is around $300 retail. But I'm not really, that's all I know at this point. Mostly, ask me again after the beta or well into the beta. I'll take one more.
So you were saying that one of the goals by doing things in SDR is getting rid of some of the hardware components that you have to worry about, working with. What are some of the primary components that you have been able to get rid of? Because it seems like, having an antenna ballast or an external clock, these are certain things that you're just not going to be able to get around.
So I think the question is, if I can paraphrase, I have a lot of crap in my bag. How much does this let me get rid of? And this kind of relates to the antenna question earlier. There's theoretically, this can replace pretty much every radio device that I've ever carried around in my bag, with the exception of antennas, and maybe a high precision clock. Although I've never carried around a high precision clock with me. In the lab, I've used them. We have so like the IMMe, the Ubertooth, the last year's TourCom badge, this year's TourCom badge, the next Hope badge, various other wireless transceiver integrated circuit-based devices. Theoretically, I don't really need any of them anymore with with HackRF in my bag. Antenna-wise, I like to have a telescoping antenna that allows me to hit a whole lot of frequencies down, well sub gigahertz. And then for things over a gigahertz, I either just use the telescope antenna collapsed all the way and just know that it doesn't perform very well, or I have a dedicated 2.4 gigahertz antenna or a couple of others in my bag. So as long as I don't care too much about performance and range and directionality, I can get by with just, kind of 2 or 3 not very bulky antennas in my bag. What's that? Heuristic?
Yeah, 80% of what you're trying.
Oh yeah, hit 80% of what I'm trying to get. Yeah, so thank you guys all so much for coming. We're really glad to be here, glad to be making this announcement here. Hang on to your cards, and we'll see you around TourCon.